Hello and welcome to this video. In this video we're now going to take a step away from all of the particle interactions or the nuclear interactions looking at radiation, and we're going to have a more focused look on the nucleus itself. Now we know the nucleus is made up of protons and neutrons. Okay, so the nucleus, if I have this nucleus, I have some positive charges, I have some neutral charges, and the combination of all of these protons and neutrons gives me my nucleus. Now, there has to be some sort of force holding this nucleus together. We know that this is held together by the strong nuclear force, because if we had no force holding these together, we know it would be the electromagnetic force that would take over, and all of these positively charged particles would just repel. So it's held together by the strong nuclear force. And now, if we have this binding energy, as the title says, the binding energy is going to allow us to describe how much energy does it actually take to hold this system together. Because surely if we've got a force being applied, we know that the force is related to energy from what we've seen in electric fields or gravitational fields or any of this. The same thing happens for the strong nuclear force. If I have some force present, it means I'm putting some energy into the system, because we know that the work done is the force times the distance. We have this kind of relationship between them. So what we're saying now is there must be an amount of energy present to hold this nucleus together, and this is the binding energy. Now, the way we define the binding energy, so our definition of the binding energy, is slightly different to how I've just introduced it, because you can imagine the binding energy as being a threshold for then saying if we wanted to actually break apart this nucleus, we have to overcome that amount of energy. So the binding energy is actually defined as the energy required to separate a nucleus into protons and neutrons, okay, into its constituent protons and neutrons. Okay, so this means now that using this logic that we know there has to be some energy to hold it together, we now have a definition of the binding energy, which means we can now measure an amount of energy that it takes in order to overcome the attraction inside the nucleus. From there, we then have to say, let's go back for a second to particle physics. And in particle physics, we said that the energy of something, so anything that has some mass, has some energy, right? Because we said that we had Einstein's equation, which I'm going to write up here, which is the energy, the mass energy, is equal to mc squared. This is a very famous equation, and it just means that energy and mass are interchangeable states. So if I have all of this mass present, I have some amount of energy present. Now this is interesting then, because it means that actually when we want to calculate the total amount of mass present in a nucleus, it's not just down to the mass of the protons and neutrons, because I also have this extra energy present in the system, the binding energy, that's actually holding these together. And I know that energy and mass are interchangeable. So if I have some extra energy, it means I have some extra mass. And we can actually apply this same idea of binding energy to protons or neutrons themselves. We find that if we were to add up the masses of quarks, we don't actually get anywhere near the mass of a proton or a neutron, because the masses of protons and neutrons, the masses of the up and down quarks, only contribute about 1% of the mass of a proton or a neutron. And that's because we have immense amounts of binding energy. Now, if we wanted to think about this in a particle physics sense, we would say that this energy that's being held together is there present in the exchange particles. So the exchange particles provide the energy to hold the nucleus together. Okay, because these are the particles that are applying the force, and therefore they're supplying the energy to hold the nucleus together. But this then means that if I were to then break apart a nucleus, say in a fission reaction, or I were to bind two nuclei together in a fusion reaction, I'm actually going to end up with some mass difference. Because if I, for example, were to have a large atom, so for example, if I scroll down here, let's say I take an atom of uranium. So uranium is pretty large, so I have uranium-235, and we know that we spent a lot of the 20th century trying to split the atom, because we know that there are these immense amounts of energy present in there from this binding energy. So if we split it, let's say we split this into I don't know, let's say thorium and radon, for example, and these two elements or isotopes that we get are smaller than the uranium-235, obviously, since we know that we're splitting the nucleus of the uranium-235, we get two smaller nuclei. This then means if we have less nucleons to hold together, it requires less exchange particles, which means actually the binding energy has now decreased. So this leads to a difference in the binding energy. Because the binding energy it requires for uranium-235 is going to be much bigger than the binding energy for thorium, and much bigger than the binding energy for radon. And actually what we find is even if we combine, even when combined, the total binding energy of thorium and radon is not close to the binding energy of uranium-235. And by this logic, that surely means by splitting the atom, we've now released energy somewhere. Because if the energy we have here is, let's say, E0, and then we have E1 and E2, where we know that E0 is greater than E1 plus E2, right? So we're saying the total amount of binding energy we start with is bigger than the sum of the binding energies we had once we split this atom. By this formula, we would see that surely we need to conserve energy, which means that actually in this reaction, so therefore in this interaction or this fission interaction that happens, and we'll talk more about fission in a future video, we release energy. So energy is released. And we can do, and this is very useful because it means that if we can successfully pull off fission interactions, which we can force, and we'll look at how we do that in a third video, we can just harvest energy from atoms. Now, this isn't the only way we can do it. We could also fuse atoms together, which is fusion, which is the second way that we could do this. I'm not going to go into fusion too much in this video, as we will look at it, as I say, in a further video. But the thing from here is then to ask, how much energy is released? Is this whole fission reaction worth the amount of energy released? How do we actually tell the difference? How can we measure an amount of energy? To be fair, we don't even know what type of energy is being emitted in this case. So how do we actually quantify the energy that's missing? Now, what we're saying here is that I've lost binding energy. Now, we go back to this formula where we say that binding energy is going to contribute to the overall mass. If I've now lost binding energy overall, I've now lost mass overall. I can calculate something called the mass defect. Okay, so the mass defect is just the change in the mass of the starting nucleus and the two product nuclei. So this is the change in the mass, which is just the total mass of the original nucleus, which would be 235 times U, where U is the atomic mass unit, so I'm going to call it the atomic mass unit. And then we're going to minus the total masses of these two combined. And when we actually calculate their masses, or we can measure their masses, we'll find that we will end up with some change in mass. Now, I haven't specified what these are, so I'm just going to put in brackets here mass of combined isotopes, or daughter nuclei, if you want to refer to them as that. And I end up with a change in mass. Now, a change in mass is measurable. I can measure how much the mass of something has changed just by putting it on a scale, essentially. Obviously, this is going to have to be an atomic scale, so it's going to be more complicated than just placing the substance on a scale. But it does mean that I can then measure a change in mass, use this mass defect to then put it back into this formula that E is equal to mc squared, and I can calculate the energy released during this interaction. This is a very common exam style question that you will be asked on binding energy. Now, I've specifically done this example for fission because that's what I see comes up the most, so this is probably what I would focus on. It is also possible for mass defects to occur in fusion because it would just be the opposite. I would start off with two smaller masses, I would end up with a larger mass. Now, in order to release energy in a fusion reaction, there's a different type of energy. So it's not necessarily the binding energy, which is why we don't really look at it too much, but we will still get some energy released. I'll talk about that in a further video. So now, how do we choose which nuclei are going to have a fusion reaction or a fission reaction? How can we actually tell? And this is where we are going to move on from here for a second and look at the nuclear stability curve. Okay, the nuclear stability curve. Now, the nuclear stability curve is quite a precise curve that we use in order to look at different nuclei and be able to tell whether they would release more energy in fission or in fusion. Now, I'm going to pull up a graph now in order to prevent me from getting the sketch wrong. And this is that graph. This is the nuclear stability curve. We see this green curve here is your actual stability line, or your average line that we go through for all nuclides. Now, you'll see that it is split around this point here, and if I change the pen so I can annotate this, we'll go with red. Each of these points are data points for each individual isotope, and we see that in general they make this curve. Now, the x-axis here is the mass number, so this is specifying that for each point we have, this is a different nuclide, or a different nucleus, which then is going to contribute to this idea of the stability. And our y-axis is the binding energy per nucleon. Okay, so per nucleon means that we're saying that on average, if we were to take the amount of energy just to split a single neutron or a single proton away from this, how much energy would it require? Now, if we have the binding energy per nucleon, binding energy per nucleon, this means the higher this is, the harder it is to split. Okay, and the harder it is to split, the more stable your isotope or your nucleus is. So this then basically is a measure of the stability of the nucleus. So the larger the and I'm going to call it binding energy per nucleon, the more stable it is. Now we'll see in this graph that we actually end up with a peak about here, which is why we've drawn this line here. This is the most stable isotope that we have, and it resides at a mass number of about 50. Now this isn't going to be a specific element, because we could get isotopes of several different elements that will all have mass numbers of 50, but when we have things around there, it means that we end up with the most stable possible nucleus. Now, from there, we say, okay, if we look at everything before this, so we'll look at fusion. So I'll put the fusion in green. So fusion. First of all, we've mentioned this word fusion a couple of times, but what actually is it? And fusion, in a very short explanation, is just the combining of two nuclei. Okay, so we combine two nuclei. And most of you will have probably heard of fusion in GCSE. But what this means is that anything below this does not have a large enough binding energy such that if we were to split it apart, it would end up giving out a considerable amount of energy, given it will still give out an amount of energy, but it's not a vast difference. If I were to, for example, say, let's start here, and I'm going to give out half of my energy, I only end up going back to here. Okay, so if I give out half of the number of half of my mass number, I end up just going from, even if I were to go and put some numbers on this, let's say this is let's take the 40 mark here, and I'm going to get to 20. Now 20 is about here. I'm only actually losing about 2 mega electron volts, maybe. Now this means that if I were to break these apart, I end up with not a very large amount of difference. Now let's say I take these two elements, the 20 and 40, and I'm going to combine these together and then see how much energy I then have per nucleon. And if I combine these, I then get to 60, and now I'm up here. So now I have a larger binding energy per nucleon. I end up with a more stable nucleus, which is going to give out a lot more energy. Hence why this is here. So more energy is given out by fusion than fission for this section. Okay, so it means that anything on this side of this red line leads to a fusion. So these things will be giving out more energy. It'd be more useful to collide them and combine them than it would be to break them apart. Then we have to change back for fission, and fission is just something that we do in order to split the atom, right? So we just split a nucleus into daughter nuclei, and we'll look again at why we can do that. Now, if we were to then do the same thing here, if I have 250 and I were to, for example, give out something that's half of that difference, I'm going to end up going to 125, which is here, and I end up with quite a large mass defect, right? And if I end up with a large mass defect, I end up with a large difference in the binding energy, so I end up with a lot of energy given out by this method. Hence, for everything above this point of 50, more energy is given out by fission than fusion. So it means it is smarter to break these isotopes apart rather than try and combine them together, because we can see if we were to combine these together, we're going to end up with a mass number that's going to come down here somewhere. We're actually going to lose stability of these things, where our whole purpose of this is we're trying to get to the most stable point. And this is then concluding knowledge so far on the binding energy. So to recap, we've said that we can define the binding energy of a system as the energy required, or the work that must be done, to separate a nucleus into its protons and neutrons. We said that when we split apart an atom in a fusion reaction, we end up with a difference in the binding energy of the daughter nuclei in comparison to the parent nuclei or parent nucleus. That means that if we have a difference in the mass, we have a difference in the energy, so energy must have been released. We then say that we can quantify that by calculating the difference in the mass, putting that into Einstein's equation of E equals mc squared, and then we get overall binding energy released. Then we said, how do we know which ones are going to be better at fusion and fission? And then we come to this nuclear stability curve where we said that the binding energy per nucleon is reference to the stability of something. The higher the binding energy per nucleon, the more stable that is, the harder it is to break apart or to combine with other things. And then we said anything below this maximum or has a lower mass number will end up being more useful in a fusion reaction, and anything above this mass number will be more useful in a fission reaction. Thank you for watching.